Okay, good morning. Why don't we go ahead and get started? So, as many of you know, this is a kind of an annual tradition as we kick off the GRASP seminar to give the GRASP faculty a chance to give sort of a brief kind of taster of some of the kind of problems that they're interested in, to give you, the students, a chance to survey the field, to get a sense of what people are doing, and maybe hopefully prompt some interesting conversations going forward. As per usual, we have way too many things to do and way too little time. So again, we are going to kind of go through this in lightning fashion, kind of like speed dating without the pressure. So for the presenters who know the drill, basically we got a timer. We get 150 seconds a piece, and then the alarm goes off, and your HDMI cable is unceremoniously yanked away. So please, we will have a chance for pizza lunch immediately thereafter. So you'll have an opportunity to talk to the presenters and get into many of the details. With that, what I thought I'd do is just give you a quick review of some of the things that we've been working on. So one of the things that, of course, that we've been doing a lot here at Penn, a variety of us faculty, is working on, oh, please God, don't let it be good. There's awful audio that goes with this video, as many of you know. Many of us have been interested in working on issues related to autonomous flying vehicles. So this is kind of a canonical example of a project that we finished up last August, which involved building a completely autonomous flying out vehicle that could be commanded at a very high level. In this case, the mission was to fly up to a building, enter the building, explore the floor, look around, build a model, and ultimately exit the building, sort of demonstrating a number of different aspects. So this is kind of an example of one of the things that we're interested in and involved with, and it involves a number of interesting kind of research problems. We're currently interested in continuing to shrink the size of the platforms that we're using, do everything ideally vision guided. If we could get down to around this, size of a couple of centimeters, and do it with even fewer sensors and at higher speeds, that would make us very happy. We're also doing LiDAR-based approaches, canonical approaches based on mapping, planning, and control, all things that are very much currently of interest and going on in the lab as we speak. Another thing that we've been doing recently, this is as part of the DARPA Sub-T challenge, but occurs in other guises as well. And there's a lot going on the slide. One thing that we've been having a lot of fun with is working with actual legged platforms. This is the Ghost Vision 60 platform, and this is us playing around with it in a mine. Actually, we ended up fielding 4 of these. We sent them completely autonomously into a mine shaft and basically just waited for the loud crashing noises. As far as we know, that's the first time anybody's been stupid enough to try that. So we're happy. A ton of interesting research issues related to perception and control for legged platforms that we're really interested in continuing to delve in going forward. How do we do that based on the kind of information that we're getting back from our vision systems, from our sensor systems, and the like? Not to mention the fact that we're doing this with coordinated systems. So a ton of issues related to distributed systems. Fusing depth and imagery is something that we do, and in the interest of time, I'm actually going to skip forward and touch on another problem that I'm particularly interested in, which is how to build much more high-level representations of space, so object-level representations from data. So this is work by Armand Shariati, where we're automatically taking information from stereo and from range sensors and pulling out semantically meaningful things, such as stairways, corridors, and the like. So anyway, interested in building high-level representations of space from sensor data, one of the many things that we're interested in. Okay, so with that, I told you this was going to go fast. I will invite up Pratik.
this work?
Yes, no, no, go ahead, go for it.
Okay. Much better, no pink anymore. So, hello everyone. I am the newest member of the GRASP Lab, newer than almost most of you, I'm sure. I'm Pratik. I did my PhD on deep learning, understanding neural networks, coming up with ways of training them faster, understanding why they generalize, etc. I am a roboticist. By my DNA, I worked a bunch on autonomous driving. And the way I think about intelligence is really, I'm interested in things that live in the physical world, that have data coming to them through the sensors, that interact with the physical world in a meaningful way. We are not just interested in systems that live in the cloud, that classify your images. Yeah? So that is the reason why I call it towards an embodied intelligence. This is different from intelligence that lives in the cloud in the silicon. It is necessarily embodied. So to give you a brief summary, most of my early work was on control, on motion planning to be particular, applied to autonomous driving, urban autonomous driving, planning in cities when you know the rules of the road, you would like to respect the rules of the road, break them in cases when you need to break them. Let's say you're stuck behind a very slow car. Most of us break the rules, so why shouldn't cars do it? The later part of my PhD work was more on perception and learning, computer vision and deep learning. And then I'll kind of close with a few feature directions that I've been working on these days. So filtering and POMDPs is a problem that most of us cut our teeth in, cut our teeth on, me too. Here is a video of the autonomous car that we built at this company called Autonomy. It started sometime in 2014, where we were like going around with a little golf cart with computers taped onto this golf cart and designing motion planning algorithms. It was deployed in 2016 in Singapore, so this is the first autonomous taxi system. You could book it via an app. Today it runs in Boston and Singapore as an app, in Vegas also, I believe. And most of this work is really on like multi-agent motion planning, differential games, temporal logics, motion planning, state estimation, etc. Where do deep networks come in? Well, the first time you implement an algorithm in your simulator in MATLAB and then take it on the car and run it, it doesn't quite work. So deep networks are a nice way of understanding data that is much richer than what you can simulate yourself in a computer. And they're a way of creating good representations that actually aid control. What kind of things are we interested in doing? Well, in my past work, I focus mostly on training neural networks as well as you can. So X are the parameters. You would like to find the best such parameters for a neural network, and you would like to minimize some kind of a loss. So this is the loss of your misprediction, the loss of your mispredictions with some regularization, etc. And in practice, typically there is one algorithm that everyone ends up using. This is called stochastic gradient descent. And this is a very, very simple algorithm. So at each iteration, it takes your loss function, it takes a gradient on the loss function, and then moves on. Despite this simplicity, almost every single neural network used out there today, this is being trained using stochastic gradient descent. And the bulk of my PhD went into answering why SGD is so special. So this work is still continuing. So we are talking about this work in more generic terms these days, which is coming up with systems that are good for continual learning, that are good for lifelong learning, and creating representations that are malleable, yet good for certain tasks. Okay? Where does reinforcement learning come in? Well, I'm not happy with someone giving me a data set that lives on my hard disk. At some point of time, you need to do better things than what the data set can give you. So you need to go out, collect your own data, right? So I cannot find if there's a tiger in the room unless I walk around. It's very unlikely that the tiger is in the room, but I will never be sure unless I walk around and find it. So there's a bunch of work that we've been doing, which is mostly on reinforcement learning and understanding RL from an algorithm's perspective, coming up with better systems for RL that translate across tasks, etc. So I'll close with this, and I'll invite Eric. If you have questions, come to my office.
So for speakers, I'll give you a 3, 2, 1.
Okay.
What? Minutes. You have 3 minutes left.
So I'll close for Pratik. I'm Eric Eaton. So one of the problems that he and I are both interested in is this idea of lifelong learning. And so my group works primarily on this. So let me give you a kind of high-level overview of it. So imagine that we have a robot in a university environment, and the robot learns to recognize things like books and monitors and office plants and other things you might find around. And then I take the robot and I move it to a different environment, like a hospital. In this case, where it now encounters wheelchairs and walkers and other objects. And then we move it to another environment and another and another. And the idea is that instead of just throwing away everything we've learned before, just like you and I, this autonomous system should build automatically on what they've already learned, both for perception, action, how to interact with the environment, how to interact with people, roles of different people. And the idea is that lifelong learning should allow the agent just to continually accumulate and build upon its knowledge. So the goals of my group is to develop intelligent agents that can, first off, be able to rapidly learn new tasks just by building on this previous information, just like you and I can learn things very quickly. Learn continually from experience as concepts build upon each other, allowing it to learn more increasingly complex concepts and be increasingly useful in the world. And so I'm not interested in robots that just do one thing. I'm interested in robots that do a whole variety of things and do them all well. And lastly, incorporating guidance from humans in interaction in real environments. And so I contend that a lot of these goals can be accomplished by allowing the machine learning system to share knowledge between its learning experiences through lifelong learning. So back in 2013, we developed an algorithm called Ella, which formed a foundation for our work going forward for a number of years. This simply takes the idea of multitask learning and kind of frames it in an online fashion. And we applied it to techniques like facial expression recognition, landmine detection, some other basic multitask learning data sets. The punchline for it is it gives you about the same accuracy as if you learn all the tasks up front, and it speeds up about 1,000 times at least over all the tasks. And for individual new tasks, the speed up is much faster. So we took this framework and we built out from it in many different directions. The first, we explored things like active curriculum selection. What happens if we give the agent control over what it's going to learn next? We looked at how do you extend this to policy gradient reinforcement learning and incorporating safety constraints on it for guaranteed performance. Instead of just learning in one domain, what happens if we have a whole variety of different domains? Like for one time we're driving, say, for example, a four-wheel vehicle, and then we fly a quad rotor, and then later we try to balance a pole in our hand and such. All these control problems have relationships to each other, although they're radically different domains. Can we transfer knowledge across them? We did some work in lifelong imitation learning, where the idea is you should be able to learn something by demonstration faster because you've already had experience learning a bunch of other things from demonstration. And we've also looked at zero-shot transfer. So what happens if you give it a high-level task description? Can we do something about it to accelerate learning? We look at a variety of different issues with this, including things like transfer across diverse tasks. What happens if you look at non-stationarity into machine learning? How do you compose knowledge together? And most critically is this in the lower corner here, real-world applications to robots. So our current projects focus on things like lifelong deep learning. We have some work in lifelong learning for composable knowledge and the idea of incorporating robust transfer over time as your task distribution changes. Primarily, we apply these to problems in robotics as well as personalized medicine. And you might see these roaming around the hall a little later. These are some of the autonomous service robots that we build in a course I teach, CIS 700, and continue on with my research group to turn into a lifelong learning platform. If anyone has questions, please feel free to send me an email, and more so when the service robots are around the hallways, please interact with them. Our goal is to deploy these 24/7, have them continually interact with people, and perform a whole variety of tasks. We're hoping eventually to launch a web interface where people can interact with the robots live, send them to do tasks, and so forth. Thank you very much.
Okay, so, okay, so the pressure's on since Eric finished early. So I'm Hsieh, and we are from the Scalar Lab. So we do anything that's related to multi-robot systems, robot swarms, distributed autonomy. What is fundamentally different about our lab is that we really sort of do a lot of things from this dynamical systems theory perspective. So what do I mean by that? So some of the projects that we think about. So this is an example of how do you leverage natural escape dynamics in the ocean in order to do energy efficient navigation. So this is actually a pretty difficult problem because oftentimes for underwater robots, you're very limited in terms of localization, communication, and then the environment is constantly changing and moving around. And so one of the ways we do this is we think about, well, can you somehow characterize what the basins of attractions are in the flow? Can you identify those boundaries? And then think about how uncertainty, either in sensing, in model, in control, interacts with these boundaries, and then think about how you leverage those surrounding dynamics to be able to do planning. So one thing that we think about is if you think about, so I'm not sure why this is not playing, but this idea that if you have, right, so the idea here is if you have a potential in a system with no noise, the particle basically just rolls down and stays at the bottom of the hill. But with noise, you actually have a non-zero likelihood of being able to get pushed out from that well. And so if you know how to, so the idea is, can you somehow design controllers that either enhance or abate and interact with that dynamic in order to get yourself to different places. And so some of the questions we ask is, what are the right set of features that you're supposed to be looking at when you're thinking about the environment? Here's another example. We think about how do you get teams of robots to be able to model, track, estimate complex spatial temporal processes. Often, so think of examples are like oil spills. If you have, trash in the ocean, where does the trash go? How do you go, think about deploying robots to go pick it up? And so the video on top is showing you the dye experiment that we ran in a float tank, which is the one in green. And then this is our big robot tank in our lab. And then the one in white and gray, that's the model that the robots are maintaining in this distributed fashion. So some of the questions we ask is, what are the right set of features that we need to be sensing, right, doing measurements on? Where should we be placing those sensors? Because most of the time the workspace is quite big and we may not have enough robots to cover the entire space. So there's some task allocation problems, some knowledge representation, as well as being able to think about how do you quantify the uncertainty so that at every point in time, the robots are always going to positions that get information that sort of maximizes the predictive power of this online model that you're trying to build. Another example is, so in any multi-robot systems, the integrity of that wireless communication network is critical for them to be able to execute whatever task they have. So here on the top animation, you're seeing a bunch of robots trying to patrol this environment, and each of them is assigned a building that they kind of have to, keep an eye out for. Now, most existing work really think about maintaining all-time connectivity, and oftentimes this is very restrictive because those communication constraints really limits how far robots can move away from each other. But if you somehow relax that requirement and is willing to sustain intermittent or even periodic connectivity, this problem can in fact be mapped to a similar problem that is actually synchronizing coupled oscillators. And that's actually a very classical problem in sort of dynamical systems theory. And the idea here is if you can actually map that onto a coupled oscillator problem, the problem of synchronizing this and creating this network with this intermittent connectivity is actually really straightforward and can be posed as a computational geometry problem. And so if you do that, then you actually end up with very robust strategies to be able to create these networks and be able to talk about how reliably you can actually transmit information from end to end. So if you have any questions, please feel free to come to our website. That actually contains all the contact information for us. And so if you want to get involved, I encourage you guys to reach out. Thanks.
Cool. I'm Michael. I'm here for the Rehab Robotics Lab, and I'm representing Dr. Johnson, who's in the middle there. So what we do is build robots to try to understand and improve the lives and pathologies of people who have various types of neural injury. Primarily we look at stroke, but other things like cerebral palsy, which is similar, we also look at. And we do that in a few different domains. So the first project that I'll talk about is this Rehab Cares project. The idea is to build a gym of systems, some of which are active, some of which are passive, that subjects or patients can come play games on to help improve their rehab. The need for this is that there aren't enough therapists right now to cover the number of patients we have, so patients go without getting the amount of rehab they should have, without seeing therapists as often, right? So if you can have one therapist with an entire gym, you can potentially project that more widely. You also have the opportunity to start to build social connections between your different patients and have them playing games against each other and that sort of thing, which can encourage better outcomes. Within the scope of that work, we are looking at the effect of HIV, AIDS with stroke, and how that affects cognitive motor interference. Essentially, if you have HIV, you're much more likely to get a stroke. I think it's about twice as likely. And there are effects there that can happen with the way you move and the way you think, and so that's not really studied. We want to understand that. HIV has gone down in incidence in this country, but is still a huge problem in other parts of the world, so this is really relevant. This is done using this haptic robot, it's a single degree of freedom robot that senses where people are, how they're pushing on it, and then allows it to react in an intelligent way to provide more resistance or more assistance to them as they play these games. Oh, there. So the next project is the Panda Gym. The idea here is that when a subject, or when a kid is born, they can have various things that happen early in life or prior to birth that can affect their long-term outcomes. Thing is that you generally find out about those things when they miss milestones much later in life. And by that point, you've missed this golden opportunity to take advantage of what's called neuroplasticity, the ability to reshape the way the brain works early on in life. So what we need to do is to find ways to assess that disability earlier so they can receive treatment earlier and you can have better outcomes. We're trying to do that by having sensorized toys, a sensorized gym, etc. And so it does pose tracking, it measures where the center of pressure of the baby is, how they're hitting this toy, and the toy lights up and makes sounds and all sorts of stuff, how you squeeze it. We're working with a bunch of people on this, and it's a project where we now have support to go test 1,200 patients, getting video from them in neonatal intensive care units, and another, I think it's 150 patients actually in the gym itself. And so we're really excited about what that'll do. And the final project I'll talk about is this Flow and Lil Flow project. The idea is that there are patients who aren't where the clinicians are, so you need to deliver therapy to them, some sort of motor therapy, remotely. Telepresence is great, but for things like motor therapy, it kind of breaks down. You can't communicate well. So what if you throw an avatar there that is not the clinician, separate person, clinician still on the screen, to help motivate that, play games like Simon Says, target touch games, etc. Then maybe that would create better outcomes, and you could start to allow clinicians and patients, rather than driving all over the place, to use this sort of platform to communicate and get therapy more often. And then you kind of see how that could get somewhat autonomous over time, and you could even extend it further. Yeah, we'll skip that. We do a project at Baxter, people play with it, and we look at how interactions develop. And then we have other projects too, using other systems of all scales. If you're interested in working with us, we need tons of help. So people who do CS, mechatronics, whatever, come find me, find the lab, you know where we are. All right, thank you.
I'm Sonia Roberts. I'm presenting for the Coda Check Lab. I'm going to go over 4 big ideas that drive the research in our group. First, we really like using simple dynamics, the same way that Hsieh was talking about using dynamical systems theory in order to control robots and systems of robots. We like to use simple dynamics to control complicated bodies. So here we have a robot with these little springy legs that's walking over a complicated environment, acting like each of its legs is just a simple spring. And a more direct application of this, it's easy to see, is a robot with springy legs bouncing up and down. But if you have these simple dynamics, then once you get a more complicated body, you can still control it in the same manner. So here we have this beautiful spined robot that's storing and releasing energy in its spine in between jumps. And you can even use an arbitrary number of little springs in each of these folds here, but controlling the entire system as one spring to different heights. And these might not look like the same kind of problem, but if you think about the robot on the left as bouncing up and down, and then you flip it upside down and shrink the world, maybe they're the same. All right, come on. Thank you. All right, so now if your environment starts to get a little bit more complicated, we'd also like to be able to use local information from our sensors directly in order to understand how we can improve our locomotion. So here we have Minotaur on the left trying to run around in the desert. Sand is very complicated, and it's difficult for the robot to sense. And then on the right, we have a robot that's pretending to be sand with a robot that is pretending to be a Minotaur, jumping on top of each other in order to test these local controllers. That same idea about using local information to get really good global behavior applies also to navigation on a broader scale. So if you have a robot here on the left, Minotaur, trying to get to a goal position using only local information from its LiDAR and not planning based on a map that it has of the environment, you can prove that you are able to get to that goal location from any initial start point on this plane. Now, that seems like, okay, well, we have little convex obstacles and fine, okay, you can see the goal. But if you have these weird concave obstacles, if you're willing to abstract them, so you recognize the obstacle and then abstract them and shrink them down to a convex obstacle, then you can get the same behavior in these complicated spaces as well. All right, so everything I've showed you so far is like a pretty consistent steady state behavior. So how are you going to link between a couple behaviors? Well, we call those transitional maneuvers, and here we have Minotaur jumping onto a stool. Why on earth would it want to do that? Well, if you give it a task where it has to move things around in its environment, it needs to be able to, get on the stool and move it around. By linking these two steady state behaviors, we can then perform more complex assembly tasks and other kinds of navigation tasks without necessarily giving up the great benefit of those robust guarantees that we get from dynamical systems theory. And finally, it would be absolutely wonderful if we could use features of our environment towards our locomotion goals rather than suffering from perturbations from obstacles. So here we have a robot in the family of Rex, which, when it encounters periodic obstacles, turns based on a function of its aspect ratio and the coordination of its limbs. So you can then choose what coordination of limbs you want in order to direct yourself towards your locomotion goal. If you'd like to work with us, please do.
All right, hi everyone. My name is Nikolai Matni. I'm a new assistant professor in the Department of ESE. My office is just upstairs in Levine 374. So if any of you want to hear a little bit more about what I talk about today, please stop by, shoot me an email. Would love to hear from you. So it's a really exciting time right now to be working in robotics and more broadly on designing systems that use artificial intelligence that interact with the real world. I mean, be it backflipping robots, realistic robotic manipulation, or self-driving cars, these are really, really impressive demonstrations of what math and robotics can do together. But it's important to remember, though, that as impressive as these things are, as these videos are, for every one of these that are up in the press, there are 1,000 other ones that that are on the cutting room floor that never made it out, where things have just gone catastrophically wrong. Right? So on top of being really fun to watch, they're a sobering reminder that these systems have an inherent fragility such that a seemingly imperceptible perturbation can lead to catastrophic failure. And so my work at its highest level just tries to understand what's going wrong here and how do we fix things, right? Depending on the community that you talk to, they'll give you different answers. Folks from the dynamics and controls community will say, well, maybe we just didn't have good enough models. If you'd given me a better model, I could have done better control and things wouldn't have broken down. Kind of on the other side of the fence, folks from machine learning, reinforcement learning say, well, we have these really data-rich environments and sophisticated learning techniques. I don't even need models. I can do away with all of that and design really fantastic control policies. My work tries to bring the two together and tries to show that it's really at the intersection of these two fields that all of our nerdy dreams come true. And I bring these two areas together by exploiting the fact that they all ultimately eventually boil down to solving an optimization problem. So what I want to end my last couple of minutes with is just by presenting some of the questions that I try to answer, but I'm not going to give you any answers. If you want to hear more about the answers, come and talk to me. So one of the core questions that I try to answer is just how well do I need to understand a system in order to safely or optimally control it? Do I have to model every single little detail about it? Or can I get away with a coarser model where I'm only modeling kind of the macroscopic features that I care about controlling? Or can I do away with models altogether and just work from learning maps from sensor state to action space, say from camera pixels to how my self-driving car moves? And the way that I try to rigorously compare these methods, and I don't have a favorite here, is by quantifying how much data I need to achieve near optimal performance. Right, so I want to bound the suboptimality of my learned policy with respect to some optimal policy had I known everything exactly as some function of the number of samples. And understanding how quickly this function f here goes down to 0 as I get more data is how I try to compare these different methods. Another question that I like to think about is how can I take these insights and ideas and then apply them to large-scale systems? So go from, say, a single self-driving car to an intelligent transportation system. Or if I wanted to apply machine learning and control to the power grid, how would I go about doing that? Or the Internet of Things? Or could I use these insights to understand how we do sensory motor control in our nervous system? Another question that I've been looking at recently that I'm really excited about is understanding how do I safely control a system that only gets to see the world through a camera. So on the left here, I have a video of a controller that kind of takes this mixed approach of learning an error model for my vision system and then designing a robust controller. And then on the right, where things are going crazy, is where I just do naive control, assuming that my vision system here, which was SLAM-based, is giving me perfect estimates. And so we see that this integrated approach actually leads to favorable behavior. Broadly, I just like to take an interdisciplinary approach to safe AI where, as I described, I take tools from machine learning and try to develop things like robust and safe learning-based control, do foundational research and just the basics of robust, optimal, and distributed control, and then also try to apply these ideas to application areas. So beyond robotics, I've looked at problems in computer networking, biomedicine, and neuroscience. And if you're interested, if you fit in any one of these bubbles, then please come talk to me, because it's really only by bringing these three areas together, control, learning, and application areas, that I think we can really develop a true theory of safe AI. And so with that, I'll end. And just, yeah, please come talk to me, shoot me an email if you want to hear more about any of this.
Come on, don't do that.
All right, cool. Hey, so I'm Marc Miskin. I'm an assistant professor in electrical and systems engineering. What you're looking at up here is a real micrograph. So this image more or less sums up what my lab is about. If you walk away from nothing else, remember this. So on the left-hand side of this image is a paramecium. It's a single-celled microorganism. You might have seen one in high school swimming around under a microscope. On the right here is not a paramecium. It's a robot. It's a robot that my group built. It walks, and I can control it. So what I want to tell you about today is partly the technology that we used to build this and what we're going to use it for going forward. So basically, our robots have two main parts. They have an actuation system that I designed for them that's based on essentially nanomaterials. So there's a layer of platinum that's just about 10 atoms thick. On top of it is a layer of graphene, a single atom thick sheet. And we can use that for locomotion to build little legs and arms so we can make walking robots. We're pretty good at engineering and designing those. And those interface with the front end of standard silicon microelectronics. So you can basically take your favorite piece of CMOS microfabrication, and we figured out a way to slap legs onto it and make it into a robot. So for this very simple robot, the electronics here are pretty trivial. There's a set of two silicon photovoltaics, so basically little solar cells. One's wired to the front set of legs, one's wired to the back set of legs. And that little white dot that you can see sitting on sort of the front solar cell all the way up, that's a laser that I'm going to use to direct light into the PVs. And what you can see is when I switch it between the front and the back, off goes this little robot that's walking around. Now, this is a pretty cool movie. If you look around the robot, you'll see that there's sort of stuff jiggling around next to it. That's dust, and it's very small dust. When you get down to that size, bumps from the water molecules around you are actually enough force to start pushing things back and forth. In fact, if you shrunk this robot down by a factor of 100, it would start diffusing around randomly. So that's how small this thing is. The other thing that's fascinating about this video is in just a few seconds, you're going to see this big gray boundary coming up. So that is... Oh, well, maybe like one more pass. See this big gray boundary coming up? That's the end of the microscope slide. So we actually don't know how far these robots walk. They're pretty robust. We drive them essentially to the ends of the earth. So here's the end of the world for this robot, and that's as far as it can go. So here's this little tiny system. What it does basically is walking. It's built with these two parts of actuation and electronic control. What's cool is we don't build these robots one at a time. We actually build them massively in parallel. So we build them on 4-inch wafers. Here you go, Mark. Little chip. That's 10,000 robots. So on each one of the little tiny chips, this chip was cut out of a 4-inch wafer, so that's about this big. On that 4-inch wafer, you fit something like 1 million robots, and you build them all massively in parallel using semiconductor technology. We dice that chip up, and you get little tiny pieces about this big. Each of them has about 10,000 robots. If you look carefully, you'll see kind of these little lines through it. Each of those lines represents one of these little columns. Each one holds, on the order of a couple thousand robots. What's cool is we can actually release all of those robots out into the real world. So I don't have time to go into the technical details, but we have a process that's relatively efficient. What you can see is the last steps of it where I'm etching the substrate underneath the robots out with chemistry. Substrate goes away, and the robots fold up into their final geometries. So not only can we fabricate robots massively at scale using semiconductor technologies, but we can deploy and release them at essentially 90% yields. You can build a robot swarm with, in principle, up to 10 to the 6, 10 to the 7 elements if you want to. So, okay, what are we doing with this? Well, one of the really cool things about this project is that all of the technology we built is designed to be plug and play with CMOS. And so while this robot's really simple and all it has are these little LEDs on it or these little PVs on it that allow it to move, it's a proof of concept. What it shows is that you can put whatever silicon circuitry you want on board the robot and it'll still function. So some of the things that my lab's designing right now are little voltmeters, little thermometers, and LEDs. And we're building these parts to do basic functions. So thermometers and voltmeters to measure your environment and change your actions on the basis of what you see, and LEDs to provide bidirectional communication. So we can tell the robot what to do through laser light, and the robot can tell us what it sees through the LED response. And so that's sort of the story of this robot, what my lab's doing and what we're building. One of the fascinating things about this project to me is that there's an enormous amount in which we can grow. And so sort of filling out this space, this is really where most of the intellectual legwork of my group is. We're working kind of across scales, so some of the things we do are in the nano space. We work on developing new materials for sensing, for actuation, all the way up to building robotic components, like how do you design robots to walk, how do you make a swarm that interacts. If you have questions, you want to talk about it, I'm also in Levine, come find me. You did, yeah, I'll get it for you.
looks interesting.
Cycle with Michael and then come back.
Yeah, that's super.
All right. So my name is Michael Posa, and my lab is called the Dynamic Autonomy and Intelligent Robotics Lab. And we think a lot about how robots interact with the world. All right, so I would say at its very core, a lot of robotics, it really is about contact, right? How is a robot going to go walk, run, locomote, somehow get somewhere, and then when it gets there, it probably has to do something useful, right? It can't just kind of stare at the ground. And there are some really sort of huge fundamental problems in robotics. If you compare the ability of modern robots with that of humans, we are just so far away. Robots essentially are afraid of the world. They operate very cautiously. They very carefully pre-plan what they're going to touch and when. And if that plan goes awry, we get catastrophic failure for many of our robots. All right. So we think a lot about sort of the mathematics of these problems and with an intent of designing control policies, planning algorithms, et cetera. And what are the key challenges? To summarize them, once we get out of the realm where we have these nice differential equations that you've probably seen in your dynamics class, your controls class, we get things like discontinuities from impacts, we get stick slip from friction. Our equations of motion lack uniqueness. There's all sorts of bizarre phenomena and pathologies that can arise. And so it's our challenge to come up with algorithms that are going to be able to address these issues. So I'll sort of give a flavor of the kind of problems we work on today and mostly pose questions. So we've been thinking a lot lately about modeling systems with contact, right? So how do we sort of develop a modeling framework that can capture impact, that can capture non-uniqueness, that can capture friction in a way that's actually computationally useful to us, right? So, there are lots of existing ideas, but they don't often mesh with our algorithms. One thing that I would highlight, something that we're thinking a lot about lately that I'm excited by is this notion of machine learning for non-smooth systems. So machine learning, most algorithms are based on gradient descent. You have discontinuities. How does your gradient descent work? I think we have a solution to that, and I'd be happy to talk about that in more detail. But we want to pass gradients through these non-smooth things. We're thinking about control design. So can we design controllers that are robust, that are stable? Can we prove something about these controllers? Maybe these controllers should use tactile sensing, right? If we have these beautiful tactile sensors, what should we do with them for something like grasping or manipulation? So how should those forces feed back into our control policy in a way that's principled, where we're sort of designing this without handcrafting every PD gain? We also do a lot of walking in the lab. So we have a Cassie bipedal robot in the lab. You'll see that if you walk by the basement of town. And so one of the questions there, and kind of building off a lot of the great work that's been done in Cod Lab, is we have these sort of beautiful simple models, right, that Sonia was talking about earlier. What's the best simple model, right? Can we come up with an algorithm that's going to design the best simple model that's both efficient and low dimensional and high performance, et cetera? Can we quantify that and design an algorithm that can develop these models for us automatically rather than relying on experts like Sonia to come up with them for us? So in general, sort of what are the themes of our lab? Well, we think a lot about non-smooth dynamics. So we think about contact, friction, impacts, et cetera. We blend that with control theory. We blend that with numerical optimization. So sort of sitting at the intersection of these three areas. I guess I ran through quickly and finished early, so we'll call it there. Yeah.
Okay, let's hope this time it works. Perfect. Okay, hello everyone. I'm Yiannis. I'm a postdoc in the Grasp Lab, and today I'm giving this talk on behalf of George. Today I will give you a brief overview of some of the research problems that we are working on. In general, we are interested in applications of control theory, machine learning, verification to autonomous systems. Of course, there are several applications of autonomous systems. We are all aware of them. It's hard to include them on a single slide, like autonomous mapping, navigation, exploration, transportation, and many others. Now, of course, when it comes to autonomous systems, there are several research challenges that we need to address that range from interaction with other agents, humans, the environment, to safe autonomy. Today, I will mostly talk about some safe autonomy problems that we are working on in terms of robotics. And specifically, the main theme of this talk is the following. So consider that you have a team of robots, and those robots need to accomplish a high-level task. Okay, this task can be an exploration task, it can be surveillance, it can be a transportation task. This is up to you to define it. Now, our goal is to ensure that this mission will be successfully accomplished and safely. Okay, so first we have addressed this problem for cases where the robots operate in known environments, meaning that someone has given us a map of the environment, and then given some mission, we can design some actions and control inputs that this robot has to apply in order to successfully accomplish this task. And here, safety essentially means obstacle avoidance, but it can be more than that. And in fact, we can also impose some temporal constraints on our system. For example, in this video, we have two robots. They need to coordinate so that at least one of them there is always in the middle corridor in order to patrol it. But at the same time, the robots have to keep a safe distance from the obstacles. They have to respect some velocity and acceleration constraints. And they have to visit some charging stations whenever it's needed. Now, of course, here, as I said before, we assume that we know the map of the environment. So the next question that we have to answer is, okay, how can we learn maps of unknown environments? And this is where semantic SLAM comes into play. And essentially, George and their students have developed semantic SLAM algorithms that allow the robots to collect semantic and metric information about the environment, and then they can build probabilistic semantic maps over which the robots can operate. And more recently, we have started working on planning problems in unknown environments. And here, essentially, the main challenge is the following. So how can we design controllers? How can we control robots so that they can safely accomplish missions in the presence of semantic and metric uncertainty of the environment? For example, assume that the robot is in an unknown building and has to find all the red chairs and bring them close to a table. Okay, but what is challenging here is that we don't know where those tables are, we don't know where chairs are, we don't know the structure of the environment, the obstacles, the walls, and so on. Okay, so there we have developed essentially an action perception loop where the robot can take measurements, it builds a probabilistic semantic map online, and then it has to react and adapt to this map as the mission evolves. And we have evaluated this algorithm through simulations extensively, and more recently, we have validated through experiments. Matthew Malense is the one who is leading those experiments, who is probably somewhere here. Yep, here he is. So in this case, for example, the robot has to operate in an environment where obstacles are being placed at locations that the robot never expects, and at runtime. Okay, so our current work is mostly focused on the intersection of learning, planning, and control and perception. So if you are interested, please come talk to us. Thank you.
Hi everyone, my name is Cynthia Sung. I'm an assistant professor with the Mechanical Engineering Department here at Penn. And our group does computational design for origami robots. So our vision is that in the future, any robot you want to make for any task, you can do it. So if you have an idea for a robot, in the future, you'll be able to walk down the street, go to a Build-A-Bot store, and the system at that store will help you design the robot you need for your particular task so that you can very quickly bring it home and use it in your own life. Of course, the system here doesn't really exist yet, so the job of our group is to figure out what we should do to make the system a reality. So one of the things we're working on is computational design tools to help people make these decisions. This is a tool that we call Build-A-Bot, which where people can use a click and drag interface to compose a robot, and the system will help keep track of geometric constraints, the kinematics of the robot, and different aspects of the robot design so that it can help predict what that robot is going to do and allow them to make sure that the design they've come up with is actually going to work in reality. So this video isn't showing, but if you'd like to take a look, I'm happy to show it later. Once somebody's happy with the design that they've created, then the system automatically generates fabrication plans so that you can very quickly take your design from virtual world to reality. And so, I don't know why none of my videos are playing. Well, so if you print out the parts from that come out of the software, then you can assemble it and have a working robot in about 30 minutes. So a lot of the work that we do is, on the technical side, is trying to figure out how we can convert these ideas into physical design. So if you're interested in computational geometry, we do a lot of work in folding algorithms, trying to figure out, can we create provable guarantees on whether we can convert certain kinematics into a fold pattern. This here is an example of a robot that we've designed that is created out of one piece and that can has the same kinematics as a manufacturing crane. We use composition ideas, and so what that means is that we can combine designs that we've already created to make sure that the functionality of the robot is valid. And not only can we combine the mechanics of the structure, but we can also combine the electronics so that all of the different pieces of our robot design work together. If you don't want to fold these patterns yourself, one of the things that we also do is work on new fabrication techniques to get these robots to self-assemble. If this video was playing, what you would see is a little robot that we've laid down as a flat sheet, and when we put it on a hot plate, then it'll fold itself and walk away. So we work on how we can leverage existing desktop fabrication technologies to create these designs that can fold themselves and have these robots available quickly and effectively. We work on a lot of origami mechanics models to see how we can figure out what these designs are going to do when we fabricate them in real life. So a lot of our models are based on energy-based models. We can figure out how the origami pattern is going to form, and we can leverage these ideas to design the actuation strategies and create very natural motions with minimal control. So outlook for the future, what are we looking at? Well, we have a lot of different areas in computation, mechanical engineering, and design that need to happen. If you're interested on the more algorithmic side, we're starting up a new collaboration with research scientists in Australia on how we can combine human interaction with evolutionary algorithms to get the best of both worlds and automatically generate new designs. We're looking at how we can leverage our origami mechanics models in order to store energy in a design itself. This video that you will hopefully see is a new result just from yesterday on how we can tune an origami pattern to store energy. And so this pattern itself, there's motors on it and everything, but all of the energy stored in the pattern itself is what allows it to jump to its own height, even though it's carrying about 5 times its weight. And if you're interested in just creating new technology, we're working with people at the Children's Hospital of Philadelphia to create new reconfigurable millimeter scale devices that will help us improve care for children with congenital heart disease. So in general, our goal is to use computation in order to take your ideas and allow us to turn them into new robotic technology extremely quickly. If you're interested in the underlying algorithms, systems, or fabrication techniques that we use or create in order to do this, please come talk to me. I'm happy to follow up with you. Thank you.
All right, my name is Mark Yim. I'm going to try to go quickly, just show a bunch of videos for 5 projects that we're currently working on. There's a robot that we're looking at for building, this is toward the end of this project, we're building a robot for human-robot interface researchers. We're building 10 of these robots that we're giving to different researchers around the country. This robot will also be in the Philadelphia Museum of Art in 1 month. For a 6-month exhibit, and we're currently, a bunch of students are working like mad trying to get this thing to be robust and do some interesting behaviors. Also, we've got, how do you make a face that's not stupid looking, that will go, do interesting things for, in an art museum is another thing that's interesting. Another project is called the Variable Topology Truss. This is a project where we're working with the group in Korea to build a robot that can essentially hold up a building that's falling down. So it needs to be large and very, very strong. There are a lot of difficult problems here. One is how do you build hardware that can expand and reconfigure itself? How do you do motion planning to do this? There's 20 degrees of freedom. How do you do motion planning for 20 degrees of freedom at the same time? How do you figure out how to do it can rearrange its topology? That's also an interesting, difficult computational problem. So there are a lot of difficult things. This is current status. Well, this is the hardware from a couple years ago. We're showing how this system can actually reconfigure the nodes. They will dock into each other. The bottom video is just getting this thing to be robust is something that we're also working on that's difficult. Also, this is also from a couple years ago. We have the Guinness Book of World Records for the smallest flying robot. Their words are the smallest self-powered flying robot in the world. Right now we have a large project to shrink this down from, it's about a quarter size down to 1 centimeter and 1 gram, and then it has to be autonomous, fly around, go through an obstacle course, pick up little rocks. It's really difficult. Cindy's also part of the project, so she's developed a folding version of this so we can make it really small, which is kind of fun. Last thing that I'll just talk about really quickly, this is a project that one of my students has just recently started thinking about. What if you need a robot in Antarctica or Europa, one of the moons of Jupiter? If you can make the robot out of ice, that might be useful. It could maybe self-repair itself. How can you, what are the design issues? So a lot of what we do in my lab is figure out how to build things, how do you come up with design methodologies, how do you build a robot that can take chunks of ice, put it together, and minimum energy and all that kind of stuff. One last thing. This was a project that one of my students and one of VJ's students got together. I think one of the great things about the GRASP lab is that students interact a lot. You see what each other's doing. This is why we have this seminar now. I didn't think this was a great idea, but they really liked it. Robots that fly around that could dock in midair, really hard, but they were able to do this, getting a lot of publications. This is going to be a thesis. So I think I want to encourage all of you to think about, when you see all these things, even if you're in different groups, work together, figure out how to, come up with these crazy ideas, and things are a lot of fun. This is my website and email address. Contact me if you have any questions.
It's just amazing all the stuff that goes on here. Amazing. So my name is Daniel Miller-Uueda. I'm the Associate Director for Education and Outreach at the